thank you for the introduction and thank you for the invitation. It's nice to be back in Vienna. Oh, which one is top? Okay. Okay, I need to figure out how this works first. Yeah, this may be easier. Yeah. Okay. So I'm going to talk about joint work with Henk. And what we're going to do is we're going to look at a certain family of interval exchange transformations with infinite number of intervals. And we are going to build skew-product systems over them. And then we are going to study the ergodic properties and basically various properties. The motivation for study of such systems comes from theory of translation surfaces. They arise as first return maps on certain very complicated surfaces, and I'll talk just a little bit about that. The methods which we use to obtain our results are more or less standard. This is symbolic dynamics and theory of essential values. And the results are going to be two non-ergodicity criteria. And we also have estimates for the discrepancy diffusion coefficients of orbits of typical points. I will concentrate more on non-ergodicity criteria. Okay, so I will try to be brief and finish on time. And if you're interested in details, this is where you can look them up in the series of 3 papers. So first, what is the system of interval exchanges we're working with? Let me start with the maybe very well-known system of exchange of infinite number of intervals. This is the Kakutani von Neumann map. So what you do, take an interval and you subdivide it, so this is a unit interval, and you subdivide it into infinite number of intervals. And if you want to have an infinite number of intervals, obviously the length have to go to 0. Otherwise, you cannot fit them into a unit interval. And then the von Neumann-Kakutani map, this is interval exchange. So you move your intervals by translations. For each sub-interval, there is its own translation. And at the end, when you apply the map, you basically rearrange them in the opposite order. So here we have domain, here we have the range. We just rearranged it. So you see that, of course, this map is not continuous everywhere and has a countable number of discontinuities. So the standard way to work with such systems is to get rid of discontinuities by adding limit points and going to a counter set. And once you do that, the system which you obtain would be the dyadic odometer, which probably many of you know well. So a little bit about motivation. So what we can do with this map is the following. We can take a unit square and we can apply identifications on the sides. So everyone knows the standard torus when you identify the opposite sides of a square. So that's what we do on these vertical sides here. This is just like in the normal standard torus. But on the horizontal sides, we now apply the von Neumann-Kakutani map. So we can do that. We will need to kind of get rid of these discontinuity points because otherwise it's not nice. But when you do that, what you end up with is not a torus anymore, but a surface of infinite genus. And so this is kind of an artist's impression of the surface. You should think about it as infinite number of handles accumulating, so they're getting smaller and smaller, and they accumulate on a point, but this point is not on the surface. So this is a singularity, which is called the wild singularity. And the surface is called the Loch Ness monster. And of course, this is not a good impression of it because you see that the surface in my picture is curved, but when you do identifications, you actually obtain a flat surface. But you cannot embed it into a 3-dimensional space, so this is the best I could draw. Okay, now, so We want to do dynamics, so we're going to look at the parallel flow on the surface. And the flow is very simple. These are just flow lines adjust at some rational slope, P over Q, for instance. So, and of course, we can decompose this flow as like in 2 steps. Instead of going like that, if you're only interested in the dynamics on the section, on the horizontal section, then we can decompose this map as first a translation by a rational number, and then going vertically. And this is applying the Neumann-Kakutani map. So this is so the system I'm going to define, the family of systems I'm going to define on the next slide is, we call them rotated odometers for this reason. You kind of check the dyadic odometer and you rotated them first by a number. So that's what I said. So basically, if you translate by a rational number horizontally, this defines for you an exchange of Q intervals where Q is the denominator of this number. This is very similar to this maps of an interval rotations which we saw on the first day. So basically, this bit, the translation, defines for you a permutation of finite number of intervals, and this is a finite interval exchange transformation of which is finite, for finite number of intervals. But we are going to look at a slightly or considerably more general problem. Instead of just checking a rotation by P over Q, we are going to check our interval subdivided into a finite number of intervals of the same length, 1 over Q, and then we're going to permute them any way we want. So we check any permutation of Q intervals, and then we pre-compose it with the Neumann-Kakutani map. So what we get is a rotated odometer. And this is like a very simple example. If your P is 1 and Q is 3, then you subdivide your interval into 3 subintervals, and it finds for you a permutation 0 goes to 1 goes to 2. Now, it is clear from the picture before that if I have a rotation, then the permutation can be realized as a flow on the surface, which I defined in the previous slide, the Loch Ness monster. But what about arbitrary permutation? So one of our results is that any rotated odometer for any permutation pi of P over Q intervals, you can find the surface for which this would describe you the first Richard map of some flow of rational slope, except the surface may be a little bit more complicated than on the previous slide. So on the previous slide, I had a Loch Ness monster, so which is a surface of infinite genus with one end. But in order to realize any rotated odometer as a first Richard map of a flow, you might need to add some extra simpler cone angle singularities on the surface. By the way, if you have questions, please ask. Okay, so what do we know about the dynamics of rotated odometers? So, depending on the permutation pi, it can be different. There may or may not be subintervals of periodic points. If there are subintervals of periodic points, there may be a finite number of them or infinite number of them. If there is an infinite number of such intervals, then you have infinite number of different periods. But in any case, there is a unique aperiodic subsystem, which doesn't have to be minimal, but it has a unique minimal subset. So the unique minimal set, if we restrict to it, then the system we obtain is uniquely ergodic. And but the whole periodic subsystem can have at most Q ergodic measures, where Q is the denominator of the P over Q. And we can also say that the aperiodic subsystem and also the minimal system, they may or may not have the dyadic odometer as a maximal equicontinuous factor. So you get a wide range of properties of this system. Now, a little bit about the ideas which go into the proof of that. So you have seen these ideas already, for instance, yesterday in CBS chalk, and also on the first day in Pierre Arnoux chalk. So first of all, this family of rotated odometers turns out that they're renormalizable. It means that you can choose a subsection, you can choose a subinterval of your unit interval, so that when you look at the first return map to this subinterval, then it has a nice property. It can also be described as a composition of a permutation of a finite number of intervals and a scaled von Neumann-Kakutani map. And what scale means, this is here. But if you continue choosing such sections, so you can choose them infinitely many times, this permutation may be different. So it's not necessarily the same permutation. So this way, starting with the unit interval and the rotated odometer, you obtain an infinite number decreasing sequence of subintervals and this first return maps, which are scaled versions. And this pi here defines a sequence of permutations, few symbols. And although these permutations can differ, the sequence turns out to be pre-periodic. Which means that when you, if you look at one period, you can compose it, and this way you get an eventually stationary sequence, and therefore you can use the methods of symbolic dynamics. Okay? Now the second part is, this is how we go to the symbolic dynamics. This is the coding of the orbits. Again, this was explained already before, so I will try to be very brief. So this is our unit interval. This is the section which we chose so that we have this renormalization. And then we look, this section is subdivided into Q intervals. Then we apply our rotated odometer map, and this interval travels around until it eventually returns. And what we choose is the big interval, also subdivided into Q subintervals, numbered from 0 to Q minus 1. So what we do is we record which interval we hit, and this way we get a substitution word. And we get a substitution word for each of these small subintervals. Okay, so this is how we get a sequence of substitutions, which is eventually periodic. And as I explained earlier, what we are going to do is basically we will restrict to a stationary case, because eventually the sequence is periodic. Now, once we have a symbolic dynamical system, we have a substitution matrix. An important property of these systems is that, well, here I have an example for the substitution 0, 1, 2. And this is the substitution matrix, which tells you how many times symbols arise in each substitution word. In this case, in this particular example, the matrix is primitive, but in general, it doesn't have to be primitive. So this is basically the main difference of these systems from the ones which appeared in chalks in the previous days. So they do not have to be primitive, so this adds a little bit of a complication when you want to prove things. Okay. So this was related to odometers, but in this talk, we're actually interested in skew-product systems. So what happens here is the following. You start with your surface, and you should think about this as a copy of this square with identifications. And now we are going to look at infinite Schwann cover of the surface defined using a skew function. So a skew function, basically the behavior of this skew function is illustrated here. So if you are in the part from 0 to 1, so you have your flow line, you follow the flow line, and if you end up in the interval from 0 to 1/2, then you go up. But if you end up here, then you go down. So this defines for us a system on the product of a unit interval and the integers. And this is called a skew product. This is also a standard system. Okay, and I didn't mention that. And we will be considering the system mostly for the case when on the interval we have the Lebesgue measure, and on the integers we have the counting measure. So this system, you can think about it as the first Richon map of a lifted flow of rational slope on the Loch Ness monster. And this this integer part basically tells you in where you end up after applying the map. Okay, so we would like to study ergodic properties of this flow, of this skew product. And what we are going to use is a theory of essential values. In particular, Klaus Schmidt wrote very extensive lecture notes about that, which we use. And what results can we, and the results we obtain for the system is 2 criteria for non-ergodicity and the estimates on discrepancy and diffusion coefficients of a typical point with respect to this. So this is just a kind of short recap of theory of essential values. What you do is, using your skew function, you define this quantity, which basically records for you how you move in the staircase. And this quantity is called a co-cycle because it satisfies this condition. Basically, this means that you can describe your flow, how it, in the respect how it moves vertically. And this is a technical condition which basically tells you that you do not have too many fixed points in this staircase. Okay, but the co-cycle which we saw before can also be written down as an unweighted partial ergodic sum. And that's what I have here. And an element is called an essential value of a co-cycle if it satisfies this condition. Basically, what it means intuitively is that if you take any positive measure set and you start applying your transformation, then if you have an essential value, then the orbit of any positive measure set, like a large part of it, would move that number of steps along the staircase. Hope it makes sense intuitively. Okay, there is always the essential value of 0 because you can check 0 here. So this is a little bit like cheating. Therefore, we are going to be interested in the case when this n here is non-zero, and we will call in that case 0 a non-trivial essential value. It has some dynamical meaning, which we will see on the next slide. How much time do you have left? So what are we interested in? So first, before we can answer questions about ergodicity, maybe we should ask if this flow is recurrent to a particular section, and this would be this 0. So that's where the non-trivial essential value is coming from. Non-trivial essential value 0 basically means recurrence to a section. So a section will be just some horizontal section. So therefore, we're interested first in the question whether the system is recurrent to a section. Then maybe we would like to know if, how orbits behave. Maybe they all go far away to infinity. This is called transience. So we're interested to know when a system is transient. And this is described by adding an essential value of infinity. So this means that flow lines go far away. Now, how do we know using essential values if the system is ergodic? Well, there is a well-known result which can be found in Klaus's notes, for instance. Well, first of all, essential values, they always form a subgroup of the integers, and the system is ergodic, the skew system is ergodic, if and only if the essential values equal to the whole group of integers. This is the criteria. Now, if we look at the case when our rotated odometers do not have any periodic points, then Lebesgue measure is ergodic for that case. We call this case a covering substitution, and if that is the case, then to determine if a system is recurrent, we can use the old result of Atkinson, which tells you that if we have an ergodic transformation with ergodic probability measure, then the skew function satisfies this condition on the integral, if and only if the corresponding skew product is recurrent. So this is the reason for choosing the skew function in the previous slide to be +1 on one half of the interval and -1 on another one, because the integral is 0, and therefore we can have some hope that our skew products will be ergodic. So in the case when we do not have any periodic points of the rotated odometer, and we look at the Lebesgue measure, the system, our skew products will be automatically recurrent with our choice of the skew function. Now we have two further criteria for non-ergodicity. The first one is purely in terms of substitutions. So you look at the substitution words, and you look at some quantity called weight, and basically this determines how far you move on the staircase following one word of the substitution, and you find the greatest common divisor of that. And it turns out that the subgroup of essential values must be contained in the subgroup of Z, determined by this integer. So therefore, if this D is not 1, you know that your system is not ergodic, your skew product is not ergodic. And I just wanted to mention that recently there has been interest in non-ergodicity criteria for interval exchange transformation, and in particular, these two papers, they have some criteria for finite case. By finite, I mean when there is an exchange of finite number of intervals. Ours is for infinite number of intervals. Yeah? No, I don't think so. Related to length of substitutions. Maybe in some kind of very complicated way. No, I don't think, no. So here is one example. This is a rotated odometer for Q equal to 9. So you subdivide the interval into 9 intervals. In this case, this is the permutation you obtain. You start with, and in this case, actually, this matrix is primitive. But when you compute the weights, you see that the greatest common divisor is 2. Therefore, the skew product corresponding to this rotated odometer is not ergodic, because the essential values are going to be in this. Can we say more? We have another criteria which is technical, and but it's formulated in terms of eigenvalues and left eigenvectors of the associated substitution matrix. So if they satisfy this criteria, and weights, they also they are related with how you move along the staircase. So if these technical criteria are satisfied, then you can determine that the essential values consist of 0 and infinity. So actually, this criterion is also applied to the example from the previous slide, so we can improve on this result that essential values are a subgroup of 2Z. So when we apply this, we actually obtain a better result that essential values are actually just 0 and infinity, recurrent 0 and infinity. And this means that the orbits go up and down along the staircase infinitely far, but they still return to the middle. Okay, and I'm almost done. Very briefly, I mentioned the result on discrepancy. So there are results, of course, on discrepancy by Adamczewski and Bertin-Delacroix, but they are for primitive substitutions and also for the generalized to this ESI case. In our case, the substitutions are not primitive. So we have to redo the proof, but it's very, very similar, and this is the estimate we obtained for the discrepancy. Okay, so here is some open problems. At the beginning, when we started this project, we wanted to find a weakly mixing rotated odometer, but so far we haven't succeeded. We haven't found any weakly mixing rotated odometers. And we also were not able to prove that they do not exist. This is an open problem. Then an interesting direction seems to develop non-ergodicity or ergodicity criteria for skew products. And then, of course, we only considered one type of a skew product function, but maybe something interesting can be obtained for other types of. And this is some references I mentioned, and thank you for your attention.